Good morning. It is my pleasure to welcome you to San Diego for the 62nd annual meeting of the American College of Sports Medicine, the 6th World Congress on Exercise Medicine, and the World Congress on the Basic Science of Exercise Fatigue. Congratulations to the 2015 Program Committee chaired by President-elect Dr. Larry Armstrong on organizing a superb mix of presentations, workshops that reflect the diversity of our membership and to highlight the ACSM's unique role as an international leader in the scientific discovery and translation of exercise science and sports medicine. I'm pleased to announce that we have 3 special sessions during the lunch break each day during the conference. On Wednesday, a session entitled Empowering Lives Through Sport, the Special Olympics and ACSM, that overviews the extraordinary work of the Special Olympics and highlighting the World Games being held in Los Angeles this July. On Thursday, there's a special session to celebrate the life of former ACSM President Jack H. Wilmore, Ph.D., FACSM. And then on Friday, a session on the Aspen Institute initiative on reimagining youth sports, project play, and the critical role of sports medicine and science. I'm hoping your schedule will allow you to attend one or all of these special additions to our conference. I'd like to take a moment to remind everyone that photography and videotaping are not allowed in any of the sessions throughout the conference. We would greatly appreciate your cooperation with this rule. Now, let's take a moment to hear about the awesome, fantastic American College of Sports Medicine.
We are diverse in many ways, and with the dawn of each new day, we strive for something more. We stretch ourselves, reach across boundaries, and work together toward one common goal: a better life for all. Whether it's ensuring the safety of athletes or getting them back in the game, improving human performance, combating chronic disease, or promoting healthy lifestyles and communities, the American College of Sports Medicine is leading the way to a better life. Spanning the disciplines of research, education, practice, training, and advocacy, the members and certified exercise professionals of ACSM work to ensure the best outcomes for every child, every adult, every patient, every athlete, every person. Our international membership unites under ACSM's vision to create a better life for individuals, families, and communities. We represent the best and the brightest scientists, clinicians, and educators committed to advancing exercise science, sports medicine, and the translation of science into practice to shape a healthier, safer future. We ignite scientific discovery, break down barriers, find solutions, provide hope, inspire the next generation of leaders, and protect lives. From vision to implementation, ACSM is an influential global force that is leading the way by positively impacting lives. ACSM-driven strategic health initiatives and collaborations with major like-minded organizations create a vast network that isn't just talking about change, it's making change happen. So we are part of something much bigger than ourselves. We are creating a legacy for future generations. We are the hope. We are the hands. We are the help. And we are the heart that imagines, inspires, and prescribes a better life for all.
Wow, amazing. Let's give a round of applause to all of us for the work of our members. Go Team ACSM! Let me first start off by introducing several individuals being recognized this year for their distinguished career and outstanding scientific and scholarly contributions to sports medicine and/or the exercise sciences. ACSM has selected 6 outstanding individuals to receive the 2015 Citation Award. They include Dr. L. Bruce Gladden, Dr. Alan R. Hargens, Dr. Mary Lloyd Ireland, Dr. Richard G. Israel, Dr. Bess Marcus, and Dr. Janice Thompson. Our highest award, the ACSM Honor Award, is being bestowed upon Dr. William O. Roberts. Please join me now in congratulating each of these award recipients. The award winners will be in attendance throughout the week and will be formally recognized on Friday evening during the awards banquet. As you see them in the halls, be sure to congratulate them for their outstanding achievements. Next, I have the honor of introducing the Wolffe Lecturer. The Wolffe Lecture is the keynote address at the annual meeting in memory of one of ACSM founders, the first president, Joseph B. Wolffe, MD. Dr. William Kraemer has been invited to deliver this year's lecture entitled The Scientific Evolution of Our Understanding of Resistance Training as We Know It Today. Dr. Kraemer is a professor in the Department of Human Sciences at The Ohio State University in the College of Education and Human Ecology. He has been a member of the American College of Sports Medicine since 1974 and a fellow since 1989. Dr. Kraemer earned his doctoral degree in physiology and biochemistry in the Department of Zoology and Physiology from the University of Wyoming, where he also completed a master's degree. His undergraduate degree in physical education and health education was awarded by the University of Wisconsin-La Crosse. Dr. Kraemer's research has focused upon resistance exercise and/or resistance training as a stimulus for understanding physiological adaptations, most notably the endocrine and neuromuscular systems. His work spans from the cell to physiological systems to whole body performance levels. He has published over 425 scientific manuscripts and has authored or co-authored 10 books, including 4 on resistance training. He is a fellow in the National Strength and Conditioning Association and a past president of that organization. His work has received numerous awards. Please join me in learning more about resistance training from Dr. William Kraemer. Dr. Kraemer, please come to the podium.
I want to thank the American College of Sports Medicine, Dr. Carol Garber, Dr. Larry Armstrong, the program committee, the board of trustees for this great honor to speak with you today. The evolution of resistance training research is both wide and long. It started in many places and has continued in times when resistance training wasn't that popular. And I think the construct of its evolution has been one of persistence and use of its understanding of the human body. Today, we honor Dr. Wolffe, one of the pioneers in the American College of Sports Medicine, as noted as one of the 11 founders and the first ACSM president, a cardiologist by training, and from my communications with people who were knowing him back at the time, he may not have known too much about resistance training, but you will see one of the other founders may have influenced him a little bit different. One of the favorite sayings I have from Dr. Wolffe really translates to exercise as medicine, and also the construct of using a team approach, where he said no one can know all the answers, and this is true. The individual and collective wisdom of the group can be effectively combined so that the whole patient-minded body, you get the rounded benefit of a total medicine in one place. So I think that he was very prophetic in these type of statements in his work. So today, in a brief outline, what I want to go through today is some of the major questions in the areas of resistance training program design. The search for strength programs became really the obsession for many individuals as well as scientists, and the analytical view of research evolution, which I'll show you we took on for this conference specifically, some of the historical milestones in its evolution, the loading spectrum for strength and low muscular endurance, power development and training, and finally, muscle fiber size and relationships and individual variations, and hopefully we'll talk a little bit about the future. So with that in mind, let's go forward. In 1987, 88, we published the symposium, and the symposium was the first symposium at the American College of Sports Medicine meeting, and when I put this together with the support of Dr. James Vogel, my then boss at USARIUM, and also with the support of John Sutton, who I got to know during OE2, who was a real proponent when he was at McGill University with Digby Sale and Duncan McDougall, who also were doing classical work in the field of understanding resistance training. This particular symposium, I think you'll see by the end, set the stage for a proliferation of interest in research and acceptability of the type of work that goes on when studying lifting weights. I must say that it's daunting. I will not be able to cover everything in this short time I have today, but I want to give you a taste for some of the evolution of where we were, where we are, and where we might be going. So resistance training is a combination of so many different things today. Basically, it's using external resistance and looking at how you can build muscle for strength, size, and muscular power. So if we grab from the weight room what we're trying to study, this becomes the challenge for scientists. Scientists study resistance training programs. It's the freedom to look at all the different elements out there, to understand what they do, how they work, and basically how we might apply them to the populations we work with, has been noted in the ACSM mission. So I think this is a very important starting point. The evolution of resistance training has really revolved around some global set of questions that have been of interest to many people over the years. That being, how do I design a workout to get stronger, bigger, more powerful, and improve body composition, or different combinations thereof, and how do I individualize it to me? The other thing we did in 1983, we came up with what we called a basic cluster analysis, and what you can see here is it came up with groups of areas that resistance training programs could be quantified. And in this case, we talk about choices for choice of exercise, how you were going to order them in the weight room, how you were going to intensify them or put resistance to them, how many sets creating the volume, and then what was the rest period lengths in this type of protocol that you use. This was the first time we came up with an overview of how we might qualify or quantify a resistance training workout or training program. Now, from the ancient times on, strength was admired, and basically the workouts to improve strength were chased after both in the gym and in the practical laboratories around the world. You can see strength is quite impressive at times. I can't lift that heavy anymore. But if we go forward, if we look at scientists looking into the world of resistance training workouts and resistance training programs, scientists tried to grab some of these ideas from practitioners. They tried to understand what's going on that we may study it to understand it better. And this has been the choice and the goal of science. Basically, I have to mention scientifically Peter Karpovich. Peter Karpovich played an important role in breaking down some of the myths of resistance training way back into the late 1930s. Another element that you have to appreciate is Bob Hoffman, who was really the guru of weightlifting for USA and had a gym and trained athletes for a U.S. Olympic team in York, Pennsylvania. So Bob Hoffman, with his books, his athletes, were dealing with kind of a subculture at the time. And at that time, the myth was you may get bulky, you're inflexible, you're slow. And all these myths kind of came about. And in 1939, Peter Karpovich invited Bob Hoffman and some of his athletes to come up for a demonstration. He challenged them to do certain things, flexibility, jumping, and he found out, lo and behold, that all the myths may not be true. He then undertook a number of studies, a survey study to see if injury was greater, and he did 31,000 individuals, lifters, and he found out that the injury rate was only 1.5%. He found out hernia was any more than what selective service looked at. He found out there wasn't really an epidemic of heart conditions. He then also looked at the fact that these guys may be dumb. So he looked at 3 universities and 392 lifters, and he found that they carried a B average and the same fortitude and persistence that you need to get in the weight room and do your workouts showed up in their grades. So it was basically an interesting phenomenon of how the industry combined with the science to try to understand each other better, and Peter Karpovich is basically to be given credit for this aspect. Now today, what we've done for this lecture specifically is a type of neural network analysis for you that you'll see a little bit later and here now. And what we're trying to do is quantify the analysis of resistance training history, and you will see how it kind of works here. Our method was to look at a network program, which is really cluster analysis. If you look at artificial neural networking, we visualize the direct citation networks over time, and then we look at the cited publications from the world of science. 5 citations was meant to be an entry level, and basically we had over 5,700 World of Science records with over 11,000 publications with over 77,000 links to try to understand the pathway of what's going on. Now from this, you can see the vertical position is the oldest, and we're limited because of the world of science, so I acknowledge the fact that we won't be able to capture everything. But the vertical position gives you the publication year. You look at the top, you're the oldest, and at the bottom are the newest. And the horizontal relationships give you referencing relationships to core interfaces amongst investigators and core ideas relative to that. And we'll review this again a little bit later to understand a little bit more about this. But it gives you the idea of the lines of inquiry and the people that have been involved. And what we really find out is that there was isolated research around the world at that time, but big things have really small beginnings. And if you look at this from 1894 to 1938, at this time frame, it really came down to this whole phenomenon of literature citations, all starting with our pioneer and well known to everybody, A.V. Hill. Thomas DeLorme then gave more meaning to the concept of progressive resistance training, and Richard Berger, who interacted a lot with Bob Hoffman and was interested in weightlifting, came through, and then we had a series of connections that all the way led down to the first ACSM position stand on progression in 2002. Now we have to tip our hat off to Thomas DeLorme, an Army captain who worked in the rehabilitation of soldiers, and because he was an avid lifter, he was very interested to use this modality to help in his orthopedic practice, both from preparing former soldiers who were recovering from injury to basically helping in his orthopedic practice. Now, he was a lifter, and what you can see here from the age of 16 all the way to the older age, here he's doing a 500-pound, 227-kilogram deadlift on a short bar. Very impressive. In fact, one time he wanted to challenge Bob Hoffman to see who could be the strongest in lifting a single weight. So it's very interesting. From this, he developed a program that got popular acceptance, and it was called the Progressive Resistance Exercise System, based on a repetition maximum program. This meant you would do the number of reps you could do at a load until you couldn't do a complete full range of motion, RM. And then he downplayed it with percentages of a 10 RM, so this is what he utilized and popularized as his progressive resistance system. Now, a fact that Dr. Todd down at the Stark Center did when they interviewed his wife actually came up with this concept and the name of this over a dinner conversation when he was preparing his early publications, which is interesting. If we look at the Delorme system, he found that basically we produced dramatic results. The people who lifted got faster, healed quicker, better performance. 30–40% were much better than those who didn't weight train. So the thing was in full bloom. You basically then got the chase for what was the ideal program. I think sometimes the mythology out there is, what is the ideal program? There are aspects of each program and individualization, but this is what we have been looking at scientifically. Richard Berger, who also was involved with weightlifting and knew of the Bob Hoffman theories of training, was the first one to really quantify sets and reps using his very classical 1, 2, 3 sets of either 3, 6, or 10 RM resistance loads to see which one worked the best. And he did this throughout his whole career, both at Texas Tech and Temple University. And basically, one of the classic studies that he first did looked at 9 different programs, and where we found some of these different aspects coming out. And again, college freshmen and sophomores, untrained individuals, he did find that the 3 sets of 6 RM was the most effective in developing strength, and in this case, in the bench press. These type of things carried on into the popular press and the popular training dogmas at the time. Now, one of the lost studies, I think, goes to, Anderson and Kearney, J.T. Kearney, who's been a member of ACSM. This is a study that really showed the spectrum, where they did squat training in 3 different zones, from 6 to 8 to 30 to 40 to 100 to 150 squats. And what he was able to show is the fact that intensity got you stronger, basically, and high repetitions created better endurance. So the two were not exact, were differential. So you can't lift heavy weights and expect to get a tremendous amount of endurance, and you can't lift light weights and expect to get a tremendous amount of strength, although both occur to some degree with any program you do. So questions arose in the 1970s and 80s, how many sets do we do? And this became a real dogma of different theories and evolution from this. And recently, in a meta-analysis, Dr. Peterson, Dr. Reed, Dr. Alvar put together a very nice idea that for untrained individuals, you needed somewhere between 2 and 3 sets to really see strength actually improve. If you look at trained individuals who are more moderately trained, you raise it up to around 4 to 6 sets per muscle group. And finally, athletes who are already highly trained, you may have to go up to 6 to 8 sets per muscle group to really gain benefit for strength when you're already highly trained. Your window of adaptation is what is shrinking, and that's where it becomes more difficult to see the gains that you're making. Now, we thought maybe there's so many possibilities. We found out, Dr. Fleck and I, back in the day when we were much more handsome, and we found out that, in fact, there are 10 to 67 possibilities of workouts. How the heck are we ever going to study all these different workout combinations? So the chase actually continued, and you can see why you have such a wide variety of programs in the literature. But again, a scientist's goal is to study weight training programs, use it in different populations, from aging, from apathy with going with regard to athletic performance, etc. So the evolution continued. Now, one of the things we were really interested in, and many were, was the aspect of how do we develop power? Well, power is highly related to strength, and what we found is that exercises had to have certain characteristics. And in this case, an early study by Robert Newton and our group Häkkinen and et cetera, we found out that if you have a bench throw, the velocity and the power continues. If in fact you hold on to the bar in this case, velocity is suppressed. In fact, what we showed is that when you hold on to the bar, the antagonists fire and you dampen the agonists, and in fact you promote deceleration probably to protect joints. So in case your type of power exercises, they can't have a big decelerative component, and this is an important feature of choosing your exercise properly. Now from this, other studies that were published in MSSC, actually students of Newton and one of mine, basically showed that there's a power load spectrum. So you may need to have a combination of different types of strength training programs in your program to gain each benefit along the way. So if you're training power only, the only thing you're improving is the high velocity, light load movement of the weight over here. So if you put both heavy and power training, high velocity training together, you can move the entire curve up and to the right. Also, what they found in this study, even at the mid-test range and furthermore there, was the fact that if you're stronger, you could 2 times your body weight in a squat versus 1.3 times your body weight in a squat, you'd gain power more quickly. So in fact, there's pre-training status in some cases aids the training of another particular variable. Now, many scientists were interested in what the physiological effects were in workouts. And what you did see was regard to the fact that we saw a lot of interest in muscle fibers. Also with hormonal signaling. Now, I'm very tempted to get into this extensively, but the time constraints would not allow me to go into every aspect. This is both complex and extensive in how it interacts with the neuromuscular system, and we could see this by just looking at this diagram here. So in fact, what we have to think about is the fact that we are an integrated system made up of so many signaling cues, and you'll see later it's the upper regulatory elements of what the program is that stimulates all these particular factors. Now, we can go back to muscle fibers in the 70s and 80s. And one of our past presidents, and I really miss her, is Priscilla Clarkson, and also Walter Kroll, who was a wrestler and a power guy. Both of these did an early study that showed the difference and was representative of others that showed endurance runners have a lot different fiber profile than strength power athletes. Then Per Tesch and Lars Larson, who I was fortunate to work with at Penn State for a number of years, came out with an idea. In fact, Per presented this back in 1982, that bodybuilders may be no different than your average physical education student, but they were still successful. So we started to see that hypertrophy can occur, but it may be not due to the same reasons that we see in the lifter populations. Now, a former student of mine, Dr. Fry, showed that bodybuilders demonstrate a smaller muscle fibers and also have a fiber profile that's different, supporting what Dr. Tesch and Larson found before that. What we also found here is that a loading spectrum exists, that probably loading in the range of 80–85% of these lifters was what was actually optimal loading to be able to develop the type of strength hypertrophy seen in these lifters. Now, one of the interesting studies that I was fortunate to be involved with Dr. Robert Sterin was the fact that he showed that this continuum that Dr. Kearney and Dr. Anderson showed and had been shown before existed, that when you lift light weights, you get endurance. When you lift heavier weights, you get more strength. But what he then translated this to was to the muscle fiber itself. And what he found was the fact that if you look here, only the heavy weights and the intermediate weights were going to give you fiber hypertrophy across the entire spectrum. If you lifted up the 25 to 26 RM type of loads, you'd see that you couldn't get the hypertrophy of the fibers. And we think this was due to the voltage charge that goes through the motor units when being recruited in size principle. Now, I want to make a note here of some of our former friends, very dear friend, Dr. Gary Dudley, who is no longer with us, Dr. Fritz Hagerman, another college member of Astute. And basically what we saw is they demonstrated a number of important things over their history. They were the first, Dr. Stern was, to show that there's a shift from B fibers going over to A, or we call now X. They also demonstrated the repeat trainability of muscle memory relative to once you are trained and then you're retrained, you can train back faster. And this was connected eventually to satellite cell development and the fine work done by a number of investigators looking at muscle memory and satellite cell myonuclei potential. Now, the shifting and rapidity of this protein was also shown that thus it's not just neural changes that are happening in the first workouts, it's also protein changes that are going on as well. I also must say that then if you look further at the loading factor, I think for the most part we see that in order to gain strength with the studies, the meta-analysis by Warburn shows that you have to be in somewhat of a heavier loading range, verifying what Fry showed for drug-free body lift builders, powerlifters, and weightlifters. Another thing that I want to give a tribute to is Dr. Dudley's work, along with Dr. Meyer at Michigan State, Dr. Dudley at Georgia, looking at, and Dr. Plautz now with NASA, looking at really the construct of using weighted T2 images, a very imaginative way to really look at what muscle is being recruited, which is important. Now, one of the things my good friend Dr. Häkkinen and Dr. Comey at Jyväskylä showed something in 1988 that basically also caused us to stop. When you're talking about highly trained weightlifters over 2 years, you see a small gain in performance, but you see a very little or no gain in the size of the muscle fibers associated with this. So there's a type of phenomenon that maybe through neural changes and other factors, small performance gains are made, but the window of adaptation is tightly filled up. Now, if you look at a very interesting study too, on look of anabolic drugs, this group really demonstrated nicely the fact that drugs work. You can see here, if you look at fibers of the 2A, if you take anabolic steroids, anabolic drugs, your size of fibers dramatically increased compared to those lifters that didn't. And actually, Dr. Francois Cady demonstrated that you get also greater myonuclear production, and you can see the fact that you have more myonuclei to support the increasing size that's needed to keep the molecular domains intact. If you look also at hyperplasia, which was a big construct in the 1970s, Galnick and Gagne and the like, we also saw, in fact, that for the average person, Dr. McCall and Dr. Fleck and the group at Colorado showed that it was probably not typical as an adaptive mechanism when they looked at this particular study. So I think predominantly we could say from Dr. Tesch's review in 1988 that hypertrophy seems to predominate as the mechanism of increased size. If you look also then at our good friend and one person that I always appreciated his consult over the years was the fact that he was the first guy really in 73 and 4 to take athletes, women athletes, and track them, a tracking study so to speak. Found dramatic increases in strength with these women and also demonstrated dramatic changes in body composition which have been legendary from that standpoint. Also, Dr. Alway demonstrated that size in women's muscle can be there, but a sexual dimorphism still existed when you compare it to a comparative group of bodybuilders relative to muscle fiber size. They also pointed out, as with Dr. Gagne's work, that maybe we can't forget about muscle fiber number, and actually this was debated and talked about way back in 1897 by Mapergo, basically from University of Siena. So we've got a lot of differences going on, but I think we understand women can hypertrophy. If you look at our work in the early 2000s, we found with 6 months of training, we found that in fact if you look at thigh gain versus arm gain, if you look at basically upper body, if you don't train the muscle, it doesn't change. The arm makes a dramatic increase. If you look at both training, you can see that both arm and thigh make gains but the arm musculature in women seem to be very attentive to, in fact, making gains relative to their trainability factors as we go along. Now, one of the things that we in our laboratory are very hep on, and you're going to have a great conference on this, neural factors, later by Dr. Deschanel and his group, who are world experts in this area, and we read their papers with great interest and excitement. And this, if you want to start reading on this one paper written by Dr. Deschanel and Inoka in 2011 is a good starting place. But size principle is a major concept in resistance training, and it kind of got imported from the neural stuff and the work of Henneman during his whole career. And this basically means to me that if in fact you recruit motor units, you got to physiologically support them, both during the exercise and in recovery. So the major issue, the major concept of size principle is so important for us as exercise specialists, because that which is recruited has to be addressed from a physiological support perspective. In our cartoon version of this, we basically showed that every time you're recruiting tissue, typically you're going from low to high threshold motor units in a active manner. So it's all these guys down here, if you think back to Dr. Steren's work, and if you put heavy loads on, they're getting the high voltage phenomenon going through them every time as a stimulus. So it's very important to understand that the neural factors, which again, you'll hear some of the world's experts here coming up next, can really get after this. And this seems to be both for the concentric and the eccentric ranges of motion in an exercise. Now, we know from our laboratory and others that you see the heavier weights need higher threshold motor unit recruitment, as you saw with the cartoon. And what we're seeing here is that you need to produce more force, more motor units are recruited, if you have them. And this is very important. What we've also seen is the concept, well, let's just go to failure. And what happens in a recent study we did, we use this construct in a very demanding protocol called drop sets with a squat, where you did 90%, 70%, and 50%, and basically you did it to failure. And we thought maybe you can trick the nervous system by differential recruitment, and we found out that that doesn't work. Basically, even when you do failure at 50% of the 1RM squat, you go to failure, you still get the same percentage of activation that you do when you do it in a drop set. So there's no way to trick the nervous system in this case to try to get more activation with a lighter weight that we've talked about in this loading continuum. Now we figured out, well, why does this occur? Well, we think it occurs because of perceptual miscues. One of my old mentors, Bruce Noble in psychophysiology, would say, you got to think about the brain. And you can see here, when you go to failure at any of these loads, you're topping out the category ratio scale here. And when you're just doing warm up, you can tell, because again, the perceptual cues of failure is a completely different set. So we use this understanding to understand how people feel when they resistance train. Now, the late Bob Hickson came along in 1980, and he came up with the concept that there might be compatibility issues. And all of a sudden, if you train both, that you're going to get a reduction in strength because it can't handle both types of exercise modes. Later on, what happened was almost 15 years later, a group of people got interest in this again. Dr. Dudley as well showed this decrease in power. And basically what happened is Dr. McCarthy and Dr. Vallis at Madison showed that, well, if you back off and you don't do as much, you maybe don't get this problem with a reduction or what was, quote, overtraining at the time. Now, our work in this area also showed that, as Dr. Steren had showed, that this occurs at the cellular level. And we saw, in fact, that if you look at the type 1 athletes that did high-intensity endurance training, you could see a reduction in the size of the type 1 fibers. And you saw kind of a nullification if you did both. And what this means is that ideally you're trying to make the transfusion distance, the diffusion distance better. So it's apropos to be smaller when you're trying to deal with oxidative metabolism. Now, again, what we found here later on with a meta-analysis that Dr. Wolffe from Tampa did, we found that everything could be kind of explained in general by the fact minutes of high-intensity exercise a day. So if you look at this, you're going to see this downward trend. As you continue with high-intensity endurance training along with high-intensity training, you get a downward trend in these different markers of resistance training program goals. And then you can see the same type of thing really occurs with regard to the number of days per week that you're combining the two modalities at the high level, high intensity. So they are impacted if not prescribed properly. In fact, Dr. Hans Selye created this distress phenomenon years ago, and we got into the concept of overtraining, and this was thought to be a case. We studied this back in the day with high intensity overtraining, where we did 10 1RM squats a day for 14 days, and we found we could reduce an individual's ability to produce force. Also, a great paper that you need to read by Musin and colleagues from Europe came up with really a guideline on overtraining. If you look at it, if you just train with acute fatigue and basically you get recovery in days, you get an increase in performance, acute fatigue is always possible after a workout. If you continue on with functional overreaching, meaning you know it's going to go down, but you're going to push down intentionally and then allow recovery to occur, you basically get temporary performance decrements, but then super compensation and improvement. Timing is a really important aspect. And finally, the big problem of making mistakes in training are the non-functional overreaching. Non-functional overreaching, you don't know what's going on with your program, you're doing it, and basically what's happening is fact that mistakes are going on and you're reducing your performance. And if this continues on, then you get into the overtraining performance, which leads to decrease. Probably as noted, this is probably more unique than what we think. So many programs have been put together, this one for doing weightlifting and running together, from a concept of periodization, meaning variation protocols. And there are many in the literature. And they have to be fine-tuned to the individual. If you look at the work of all the different investigators looking at this, you have linear, nonlinear, many different ways to vary the stimulus so that you don't get into one of these non-functional overreaching scenarios. The work of Dr. Stone and his work over the years with weightlifters and classic periodization, Dr. Haff and Tudor Bompa, basically have given many different models that have been used for both sport and also recreational training. But variation is really the key when you're talking about this, along with individualization of training. We go back and we looked in 1987. We were the first to really look at short rest, the rest period issue. And all we found here was the fact that we had bodybuilders and powerlifters doing a workout. And we found out that basically the 10 short rest protocol, we had 10 exercises, short rest protocol, and what happened was the bodybuilders could drive through those workouts like nothing. It was really the cut phase of their training program. The powerlifters could drive through it with symptoms, but basically what happened was they used a much lower percent of their maximum strength to get through the workout. The untrained college type of students couldn't do it. Too many symptoms. So what we found out was over time is that this is shows you how important acid-based buffering systems are. This is what allows people to train up, so to speak, in a progressive manner to understand really the fact that protocols like this are useful for high-intensity endurance, but you have to have time to train up some of the underlying systems that mediate your ability to perform them. Individual variations have been a hot topic, and I think Monica Hubble will talk about this. Dr. Hubble will talk about genomics, but we found out early on from Dr. Bouchard's work that differences in adaptations in muscle size and strength are really related probably to individual variation, and this is really important to understand. Dr. Bamman's group was the first to kind of break out the different groups of women in this study and showed that there's differences in women, how they progress bipartisan training with the muscle fiber growth and also the satellite cell production. And you can see that not all women with hypertrophy are developed the same number of satellite cells as we had seen before in other studies. So you have responders and non-responders to workouts, to workout protocols. Now, individuals need more intense programs, as Dr. Bamman states, or maybe longer. This is the challenge of understanding the individual variations. Now, one of the things that kind of lost in the literature, and our work continues in the pituitary somatotroph area, is that you don't have one growth hormone. You got hundreds of growth hormones, more importantly aggregates. If we look at the band 2 type cells that produce the aggregates, they create the biggest constituency in your blood, and that is aggregate GH, which ranges at 2,500 microliters. In the strong women, we found 1,500 in the weaker women, versus immunoreactive, which is just piddly relative to the amount there. And this is an area of study that is going to be more important as time, because these aggregates form what we call functional amyloids with growth factors inside of them. So I think it's important to understand individual variations have underlying biological, physiological, endocrinological, molecular pinning that go along with them. We also looked at a construct of basically, what about the poor man's genomics? And we looked at extreme somatotypes. And we found in this extreme somatotypes that, in fact, we see the mesomorphs over a 6-month training could gain a lot more change in their thigh muscular area compared to ectomorphs and endomorphs. And this was for the thigh. We also saw this for the arm. So it seems at this point in time in the evolution of our understanding that their limiting factors for size and strength seem to be the number of muscle fibers, the number of satellite and mononuclei you can produce, and the type of muscle fiber. Now, Dr. Bamman postulated maybe at about 25–30% gain in fiber size, you need to be adding more nuclei. And if you can't, you may have an upper limit. Muscle fiber number, very important, as demonstrated by that. Now, we created a construct of the regulatory variables, and all I'm saying here is the fact that exercise stimuli, the program you're using, the nutrition, the environment, psychology, all these things penetrate down to the cellular, molecular, and genetic level. So the programs that you do, and why scientists study programs, is to understand how they work in this particular system and how it looks. So this is really an important construct. What we do above and how we eat and what we do does make a difference with what happens below and what mediates the changes in strength, power, size, body composition that we've been interested in over the many years. So we've not talked, we've not talked about the scientific evolution. Let's take another quick look with regard to the study of this. We utilized, again, remind you, we utilized this quantitative kind of artificial neural networking of available science to really pull together the lines of research that we see across the different barriers. So you can see, again, these are all linkages, you know, all the way from the different areas, and you can see the references and the study areas that combine from oldest to newest. You can see this whole thing from the vertical to the networking potential here. So, how has resistance training been studied? Look at what we see here. These are key words in the phenomenon of this neural networking that go from a whole host of different things, from pain, health, torque, isokinetic torque, bench press, all these different body composition, diet. This is the universe of resistance training research that we now know and live within in this global understanding of its effects. Also, today, the scientific study includes so many different networks of people interested in certain things. And the only thing I do want to say, it's important, again, that we always think about the upper regulatory elements and the program design that we're studying, because it has a direct effect on our molecular studies. It has a direct effect on our genomic studies that we're doing. And we have many investigators, of which many esteemed colleagues are in the audience today, and all of you, from if you're just starting off as a student or you've been doing this for 40 years, as I have, it's something that we got to keep in mind. But analysis looks today, we got too many to discuss, and I was overwhelmed with the topic, but we're giving you a feel for the networking that exists. There are 5 overreaching areas of emphasis. Number 1, the applied performance domain. And this is where the literature really sits in here and goes from there. We also see another non-physiological mechanism. You can see there's some overlap. There is some overlap. You then go to the next domain of looking at clinical aspects. I remember doing a study at Boston University with Avi Feigenbaum and the group up there where we looked at cardiac rehabilitation. We looked at patients being able to do lifts with over 70% of the 1RM, and it was unheard of. So I think the bottom line is we stretch our understanding by looking at what might be possible with the different protocols we use. Metabolic disorders related to body composition, etc. And finally, bone health and women's health, we've just touched on briefly today, and also aging, which is so important as we go forward. So these 5 overlapping areas, you can see there's overlap, there's interest, and basically we have to again understand the upper regulatory elements and size principle as the basis of what we're trying to accomplish when we do our research programs. So resistance training has occupied an increasingly large publication space. So if you look at this, and I can take a point from my good colleague, Dr. Armstrong, and give you a thermal view of it, you can see that the history and the publication of this area, majority have been published in these 3 journals with regard to the amount of data related to resistance training and exercise. Now, ultimately, resistance training, we've just started to gaze into the world of understanding and improving our understanding so we help practices. Scientists study resistance training protocols in order to better apply them. And we have 10 to the 67 possibilities. We characterize, we try to understand, and we're trying to do this every day in the search for this understanding, which promotes all of us to really be in this field and be excited about discovery is what the key is. And I think what holds for the future? Well, in our laboratory, we love all the molecular stuff we've talked about, and now we're going to link it up with, in fact, the full system working as one. And I think there are some great laboratories around the world. I said hello to Dr. Anoka today. There's just some great things coming in the future. We hope to be a part of that. In 2012, we published a paper showing that the cortical brain actually is sensitive to the acute program variables, so that it's not something that's obtuse or different. We can see, in fact, that the cortical brain reacts differently with a 95% when you do sets of 3 at heavy weights, sets of 10 at 80%, or power exercises at 30%. You see differences that occur. We can do so much more now with this whole neural networking and understanding of the body, and you can see this with regard to a little capture here that we have. We can actually look at the source of the impulses. We can look at the EEGs. We can then coordinate how that's going to face to the EMG and connect that along with what's going on in the blood at the same time. And we can then get a handle on really this intact, integrated system that we've been chasing for all these years. If we look at at heavier weight, we can see already in our little experiment here that you see, in fact, the differential already with regard to what's going on in the brain, in the cortical brain, in the transmission of impulses and how it works and how it goes from there. We can get heavier, and we can see 90%, and we can see again that it's a dramatic difference. Again, reflecting what we've seen before, but knowing that the upper regulatory elements in our configuration and understanding of the program is vital for our understanding of what's going on biologically and physiologically and neurologically with what we're doing with the whole program that we're studying. Finally, we go back to looking at where we've come, and you can see from the 1950s, the research has slowly increased with regard to what's going on with regard to the different aspects. And if you take a look from our little 1987, you can see that we hope we were part of the idea of increasing interest and acceptability of having a weight involved in a publication. But then again, how that weight's involved and how we look at it is very important. There are many different options that we need to look at. So finally, in summary, I think the science of resistance training has evolved due to the challenge of understanding strength, power, muscle size, and local muscular endurance, and how we've achieved it in the weight room, what we've learned from the weight room, how we've taken it to the lab, how we've interacted, and how we've worked over the years in a cooperative venture to better understand what's going on for the benefit of those that we're responsible for training, etc. Also, the novelty of human adaptation has driven us to look at greater understanding of the underlying mechanisms that mediate these adaptations, and we're living in the age of the brain as well as genomics to understand this whole integration of individual variation. And finally, the ultimate workout programs that we look at, we've pushed far ahead sometimes. The gym sometimes pushes farther ahead than what we can keep up in the laboratory, and that's our challenge as scientists. But in reality, we want to understand resistance training so we can prescribe it better, be more effective, be more, just make it better for everybody around. Because I think of the little guy or gal in the weight room trying to achieve what they want to achieve with the modality. And the modality is unbelievable, folks. It's seen it do so many things over the 45 years I've been involved with this type of stuff, from helping older individuals when we talked to Bill Evans in 1984 at Tufts University and the categorical classic papers that came out of there. When you look at special populations, when you look at the military and all the good work we're trying to do in rehabilitation, it's just amazing what the modality can do and how we've evolved. And we live in very interesting times right now. We live in a very interesting phenomenon of scientific capability and really communication. I think we got to look at the positive things, and we got to keep positive to try to keep in mind what our goal is. And I think this is very important. I have a few acknowledgments I'd like to make here at the end, and that is to Carl Marish. I'm a friend over 40 years. Supported me back in the day when I was interested in this, when at the time not too many people did. Steve Fleck, my colleague and friend who I played football with. Dr. Hackenden and I, 2 weeks apart in age, have been linked at top. Dr. Newton, a postdoc. Howard Knutkin, my boss at Penn State, who told me to speak slowly today. And James Vogel at Usarium, and John Patton, Bruce Noble, who was my mentor at Wyoming with regard to the physiology, and Randolph Lewis in biochemistry, and friend Wes Heimer, who we work with growth hormone with. These people have been exceptionally important. I think a host of people helped with the presentation today, and their names are there, and I'm very grateful for all the comments and help that we've gotten seen. For all my former graduates, postdocs, undergraduate students, you know who you are. I live and breathe each day in my daily experience with you and for you. And finally, to my current doctoral fellows, Sean Flanagan, William DuPont, Tim the Civic, and Dave Hooper, you've been a great deal of support for everything we've done and how we've tried to do it. And finally, to you, the members of the College of Sports Medicine, you've been a source of great excitement over 40 years as a member of this organization. And I think in reality, we've come a long way. We've got a long way to go, but I think in reality, I think we're going to get there. I'm excited, and I hope that you will understand today just a little bit more of where we come from, where we're going, and I thank you so much for your attention and for all your kind words. Thank you very much.
Nice job. Dr. Kraemer, on behalf of the American College of Sports Medicine, we'd like to thank you for the honor of providing the 2015 Wolffe Lecture. As a token of your appreciation, our appreciation, we would like to present you with this plaque.
Thank you very much. Thank you. Thank you.
And we wish you continuing success. I think we have to. Thank you. Thank you. Thank you, everyone, for attending. I'll just remind you of our midday special session. You have the information on your desk. And have a wonderful day.
Thank you.
Your seat.
Thank you.
Great job.